So we're going to talk about category theory and how we can use it as a tool to think about functional programming. But before we begin, I'd like to start with a small intro just to get us into the right frame of mind. So if you happen to be following the Haskell ecosystem, you quite likely have heard about Edward Kmet. And I will use him as an example of someone who's very proficient in category theory and the sort of person that inspired this talk. So this is a somewhat edited quote from the Haskell Reddit. And there someone was describing some new and useful idea for functional programming, and Edward points out that this is just the right con extension encoding of something other well-known before. And when saying something like this, although I have no idea what a con extension is, the first thing that comes to my mind is is there a left con extension? And can we use it to can we use it to derive something equally useful and impressive as well in functional programming? But delving deeper into this quote, this reveals something very, very profound. And this is, we see an example of applying a technique from category theory to derive one idea from another. So this is an example of how category theory can be used as a tool to explore what I'll call the idea space. So what do I mean by the idea space? There are lots of useful ideas in the world, some of them in the world of functional programming. And every once in a while, someone comes up with a new idea, a new major idea. And maybe if we're lucky, we can derive some other smaller ideas, not as major, but also useful as well. And then somewhere else, someone else discovers another idea with its own follow-up ideas. And rinse and repeat as many times as you want. And this is what I'll call the idea space, the space of ideas that we can discover about various topics. So the problem with the pictures that I'm drawing here is the fact that discovering each idea here requires some special insight, eureka moment or stroke of genius. And once you discovered such an idea, there's no, typically it won't help you discover other significant ideas just as significant as the one you just discovered. So how can you connect all of these differently shaped ideas? How can you figure out that, say, this circle-shaped idea is related to this square-shaped idea? It's probably not obvious, and there is no generic way to just move around between ideas like that. So what I want to say here is that we're lacking the tools to explore the idea space. In this talk, I'll try to show you how we can use category theory to provide us with various tools that will help us connect the various ideas and help us with this exploration. And using techniques from category theory, we'll be able to connect these ideas and sometimes even discover brand new ideas just coming out of these mathematical techniques. So category theory will help us discover new ideas in a way that help us explore the idea space in a way that's much more systematic, mechanical, and much better suited for discovery than just sitting around and waiting for a stroke of genius. So here's what I'm going to talk about. So I'll start with a very, very quick introduction to category theory, just the bare basics that we'll need for the purposes of this talk. Next, we'll see how we can translate ideas from programming to the language of category theory and see what new insights we can gain from it. Then we'll build on this knowledge to help us recognize categorical structures in various things around us. And this, again, will lead to new insights about these structures. And the last class of ideas is, the last class of techniques that I'll try to show you is how you can generalize an idea, make it portable between categories, and see how we can discover brand new structures just by moving around categories. So hopefully by the end of the talk, you'll be inspired to approach category theory on your own and use it as a tool for thought. Just a quick show of hands. How many people here heard of category theory before? Okay, how many people have attended a talk about category theory or read a book or something? Okay, quite a few. And how many people are using category theory in production? Whatever that means. I envy you. Okay, wonderful. I have no idea what it means to use category theory in production, but okay. So we'll start with the very, very, very basics of category theory. For the mathematically inclined here, please be advised that I'll be very loose with some of the definitions, especially with the absence of most laws. Please don't judge me for it. I mean well. So let's start. So what is a category? So a category consists of a number of things. We have a bunch of objects. I'll call them A, B, and C, for lack of a better name. we have a bunch of arrows, which are called morphisms that go between the objects. These arrows or morphisms must behave nicely in the sense that they compose. So given that we have a path like this from A, B to C, we must also have the composite path that does exactly the same thing going between A and C. So this is maybe quite abstract because objects and morphisms can be pretty much anything. But since this is a programming conference, we'll focus on the first category we'll start with is the category of types. So the category that is formed by the types in our type system. Specifically, our objects are going to be various types. So integer, strings, booleans, and any concrete type in our programming language is going to be an object in our category. And morphisms are going to be just functions. So a function from integer to a string is a morphism between the object integer and the object string. And now function composition will give us the correct behavior that we expect a category to have. So given the definitions that we have so far, what is category theory about? So for the purposes of this talk, it's about composition. So since it's pretty much the only structure that the category has, then composition must be something quite important from the perspective of category theory. And as programmers, this should be very, very interesting to us because working with things that compose are probably is probably the nicest thing to work with, especially if you're doing functional programming. But more importantly for this talk, category theory is about relationships. That is specifically how things relate to each other. Notice how in the definition of a category, we didn't talk about the specifics of objects. So we don't care that integers are made of bits or strings are made of characters. All we care about is that these concepts exist and how they relate to each other. So what morphisms they have coming and going between them. So thinking about how things relate to each other is exactly the sort of thing that we'll use to be able to explore the idea space. So let's begin. So now that we know what a category is, we can try to convert concepts from programming into the language of category theory. That is, we would like to talk about them only in terms of objects and morphisms. Once we manage to do that, we'll see how useful this point of view is. So we'll start with tuples, one of the simplest concepts in programming. So a pair of two types. So this is how mathematicians designate a tuple. So we say it's a product of A and B. Since category theory is about relationships, the first question to ask is how does a tuple relate to anything else? Well, obviously, because a tuple contains an A and a B, there must be a way to extract an A from it and extract a B from it. We call these morphisms projections. So we can project an A from a tuple of A and B and project a B from a tuple of A and B. Now, there are lots of things with this property. Many things can be projected into A and B. For example, suppose we have some other candidate, tuple candidate, that pretends to be a tuple as well. So it has its own projections into A and B. How can we differentiate our product type, our tuple, from any other candidate? So what we would like to find is sort of the best fit for being a tuple. I just want something that's not too big and not too small. It contains exactly A and B and nothing else. So one way to do this, to achieve this goal is to build what we call a universal construction. So we do it as follows. So we draw an arrow. This is called a universal arrow, and it'll be marked as a dashed arrow all the time. So the universality in this case means that there's exactly one arrow like this pointing from our candidate into our actual product type. And the resulting diagram is called the commutative diagram. This means that for any path that we take from one point to another, all the possible paths that lead us from the same starting point to the same ending point must yield the same result. So in this case, this means the following. So if we start from C and go to A via the projection from C, or we go from C via U and then P1, we'll get the exact same result. And the same goes for the other side. Now, since U is universal, there must be exactly one way to do this. So there will be exactly one U that satisfies this property. So this precisely, although not obviously, but precisely captures the notion of being a product. It'll be exactly the right fit for the size of a tuple. It won't be too big or too small. Because if our product type was too big, there will be more than one morphism satisfying this property. And if our product type would have been too small, there wouldn't be any morphisms satisfying this property. So this is the categorical way of defining a tuple. And as you can see, we're defining it by the way it relates to other things in our category, by its relationships to other objects in the category. And And what we don't care about is implementation details. I don't care how you represent A and B in memory and what exactly are you doing in your programming language. What I care about is are the relationships. And this may seem like a rather roundabout way of defining something as simple as a tuple, but we immediately gain something useful in return. So by talking about these relationships, we can use the fact that relationships can be reversed. Quite literally, we can take all the errors and reverse them. So by doing this completely mechanical act, we just discovered something new. This is yet another commutative diagram for another new concept, meaning that we have discovered something new just by reversing errors. So the question is, what is this thing? Well, it says that you can put an A into it, or you can put an B into it, and it's also the best such thing that can have either A or B. And that's just a clue to what it is. It's exactly the either type. So it can be either A or either B. And it's defined via its relationships to other things. So, and programmers call it the sum type, hence the plus here. Mathematicians, sorry. So this is quite amazing because just by doing a mechanical transformation of some diagram with almost zero effort, we derived a new concept from another one. And this is part of a more general principle called duality. So duality gives us ideas for free. Once we formulate a concept in a categorical way, that is using its relationships to other things, we can invoke duality, just reverse all the errors, and get another concept for free, just by doing this reversal. This is completely mechanical, and sometimes dual concepts are not obviously related. And we get all this for free just by taking the categorical perspective. So from now on, for pretty much any new concept that I'll introduce, you can take away two concepts from it. And so this is our first tool to help us in the exploration of the idea space that I mentioned before. But let's talk more deeply about these universal constructions that we just saw. So if you go down the path of defining concepts categorically, which you should definitely do, it's a very interesting thing to do. Universal constructions crop up quite a lot. So we just saw the product type, but there are more. And each one of those can be a useful and interesting concept. But if you look at them more closely, there's something a bit repetitive here. There's always some kind of best object hanging above some pattern of other objects, and there's always some other candidate going with a universal error into it. And as a programmer, I find this repetition to be a bit annoying, kind of like code that's not dry enough. But fortunately, it seems that mathematicians are very, very good at discovering patterns and kind of distilling their essence. So that's what we'll try to do here. We'll try to kind of have concept reuse of sorts. So what do we have here? So in each universal construction, we have some category that we're interested in looking at, and we're trying to single out a pattern from this category. So we'll use another tool to actually single out the pattern. So we'll use what we call an indexing category. So in this case, we're trying to single out a pair of product types. So we need two objects in our indexing category. Since we're trying to describe the product pattern, we'll have to kind of map from our indexing category into our target category. And we'll do this like so. We just draw a couple of arrows each. So each object in our indexing category is pointing into some object in our target category. More formally, we're building a functor here, but I won't be delving into that anymore deeply. But we call this construction a diagram of the indexing category in the target category. So this covers the pattern in the universal construction. So this is our way to single out patterns inside various categories. So let's zoom in on this pattern. So we look only at the pattern that is required for product type. So this is just these are just some two objects in our category. Now we must find the best object. So the best object must have morphisms pointing into our pattern. So our best object has, in this case, two morphisms pointing into our pattern, and this is called a cone over the diagram because it looks like a cone. But now we want it to be the best object. So in order for this to be the best object, we must have other candidates that go for the same role. So suppose we have many other cones. So these are all candidate cones that are trying to be the best cone over the diagram here. Because our one is the best one, we'll have a universal error pointing into our cone. So we call this object the limit of the diagram, and it will be the best object in the role of a cone over the diagram. So now this captures all the parts of universal construction. We have the pattern, we have the best object, and we know that it's the best because we have a universal construction here. In this case, we just re-described the product type, and this may seem like we just swapped one universal construction for another, but we immediately gain something new. In this case, we can now just draw some simple pattern, and this small picture represents the whole universal construction that we had before. So now it's like kind of draw a picture, get a concept. Actually, by duality, for each picture that you draw, you have two concepts on your hands because for each limit we have also the dual co-limit. So we managed to minimize each concept to its very, very essence, and I find this very compact representation quite satisfying. And we can draw more diagrams, for example, these do. And although I won't be going into what they mean, you feel free to actually figure out what it means in the world of type systems. We'll just look at this one last diagram, the empty diagram, which may seem a bit trivial and kind of useless, but it's actually quite interesting on its own. So let's try to build a universal construction from this empty diagram. We start by drawing a cone over the empty diagram. So a cone over an empty diagram is just an object because there are no morphisms, no object to point into, there are no morphisms. Now we want to say that for every other cone, so it's any other object in the category because every object is a cone over the empty diagram, we must have a unique morphism pointing into our limit. And we call this object the terminal object of the category, and we mark it with 1. And of course, because by duality, we also have the dual concept, the initial object. So we have another object called the initial object. And so for every object can be uniquely mapped into the terminal object, and every object in the category can be mapped into uniquely from the initial object. So more concretely, in the category of types, the terminal object is the unit, type with a single inhabitant, and the initial object is void, the type with 0 inhabitants. In some sense, the initial and terminal objects are kind of the endpoints of a category, and so they may be they can be used as a good place to start exploring new categories, which is exactly what we'll do next. Okay, so far we've been looking at the category of types. Now I'd like to look at to search for other categories and look at them and see whether we can learn something new from the categorical structure that we'll discover. So we start with monoids. Monoids are quite common in programming. They're the essence of combining two things. So a monoid gives us the ability to take two values of type A and combine them into a single value of type A. And there's also the empty value, which kind of disappears during combination. You notice that this is not the standard way of describing monoids, but it'll be more convenient for us to draw a diagram of it. So let's do exactly that. So suppose we want to define a monoid over some type A. So a monoid over some type A must have a morphism pointing into it from a product of two A's. So this corresponds to our combination function. And it also must have a morphism from the unit value back into A. So this corresponds to our empty value. So I'm cheating here a bit because I said before that the category theory doesn't care about the inner structure of objects, so we can't really reference the innards of A. But by using functions from the unit type, which are just correspond to constants, we kind of work around this and reference elements of A nonetheless. So this is the categorical way of referencing constants. Now, since we now have a diagram, we can actually reverse the errors and discover the comonoid, and you feel free to figure out whether it's useful for anything or not. But in this case, I actually want to do something else. I want to build a category. Specifically, I want to build a category of monoids. So in this new category, the objects are going to be monoids, obviously. And the question is, what are the morphisms going to be? So suppose we have two monoids, one monoid over A and one monoid over B. So a morphism in this category will be called a monoid homomorphism, and it's now denote them with squiggly arrows. And since we're dealing with monoids, a homomorphism must respect the monoidal structure. Specifically, this means the following. So a homomorphism must map the empty value from A to the empty value from B. So this diagram has to commute. And also it has to respect the combination function of the monoid. So for example, if you have two A's and want to combine them and then apply H, is the same thing as applying H to both values A and then combining them with the B combination function. So again, so any function that makes this whole diagram commute will be a homomorphism, and quite conveniently, homomorphisms compose. So if we have two homomorphisms, we can build a bigger one from them, and every time we see composition, there may be a category lurking around. And that's exactly the case. So behold the monoid category. It's a category with objects as monoids and homomorphisms as morphisms between our objects. And can we learn anything new from this category? Well, there is something interesting going on. This category is obviously related to the category that we started with, because it's just the same category of types, but with some added structure that lives above it. Since category theory is so naturally equipped with, for analyzing relationships, analyzing this relationship might yield some interesting insights. So in this case, the relationship is about forgetting. If we forget the monoid structure, we get back the original category, the same object and the same morphisms from the category of types. Now, when we talked about duality before, we talked about reversing the relationship. The question is, can we reverse the relationship of forgetting? And the answer is unfortunately that no. If you forgot something, remembering it back might be non-trivial. So for example, one type in our original category might correspond to two different monoids in the category of monoids. So unforgetting is not something that we can just trivially do mechanically. But what makes this category even more special, the category of monoids, is the fact that the homomorphisms are quite special. So only a small fraction of the functions in the category of types will actually be homomorphisms. And the question is, how can we deal with those in the process of unforgetting? So let's focus on some specific function. So suppose I choose at random some function that goes from A to some monoid D. F is quite likely not to be a homomorphism, so that's not a way of remembering monoids from A, but maybe it can be decomposed into parts. So suppose we decompose A into part G and a part H here. So that this triangle commutes. So going from here to here or from here to here is the same thing, yields the same result. Now we have G, which is still a regular function from A, but H is a homomorphism. And we can think of it as a sort of homomorphic part of F. Maybe if we focus on this part, we can sort of unforget ourselves back into the category of monoids. But unfortunately, this decomposition is not unique. You can decompose the same functions in other ways. So, for example, the path through B here is another decomposition of the F function via other homomorphisms. But the suggestive way in which I've drawn this diagram is kind of meant to suggest that there's something lurking around here. So if we think about these functions from A as sort of steps towards the monoid world, so each function takes us into some monoid, and sort of our first step towards remembering some monoid, then each homomorphism here that decomposes the function is a way to move between steps. And since homomorphisms compose, we can, this movement between steps also composes. And now this should be our cue to start looking for a category. Since we're seeing something that composes, there might be a category lurking around. And indeed, there is a category here, a rather weird one. It's a category that is formed by functions from A. So every function from A to some monoid will be an object in our new category, and the morphisms are going to be homomorphisms that decompose them. So each homomorphism that forms a commuting triangle like the one here will be a morphism in our new category. So this category should somehow embody the notion of unforgetting monoids from A. So for some obscure reasons, it's called the comma category in mathematics. But maybe if we explore this new category, we can learn something about the process of unforgetting things back into the monoid world. So as I mentioned before, a good place to start exploring categories is by looking at the initial and terminal objects. So let's take a look at the initial object in our new comma category. So because the objects in the comma category are functions from A, the initial object is going to be a function from A to some monoid, which I'll call I for initial. By the definition of the initial object, for every other object in our category, so here we're pointing to some other morphism, some other monoid in the category of monoids, there will be a unique homomorphism pointing from our initial monoid into our target monoid. So we just discovered a new universal construction. So the combination of a new category and an old concept yields a new universal construction, and so a new concept. But what is this thing? is it useful for anything that we can actually, as programmers, do something with it? And this is actually the part of one of the bigger challenges of using category theory for anything, is the fact that we must figure out on our own whether a new structure that we just discovered is actually useful for anything we care about. So let's try to do exactly that. So we'll just analyze this example and see what it corresponds to. So for concreteness, I'm going to choose A to be the unit type, and the monoid is going to be integers with addition. And I'm going to choose f to be a function that returns 5 for the unit value. And so what do we have here? So I'm going to call this function for inject, because it injects into our mystery monoid. And so the result of injecting unit into our mystery monoid is going to be left as inject unit, just because I have no idea what it is yet. And so since this is a commuting triangle, so both paths are equivalent, we can we have the following relationship. So first going with f into the monoids, which yields 5, is the same as going through inject first and then applying h on the result. So we have an equation here that we can use to figure out what's going on. Also, because h is a homomorphism, we know that it must preserve the empty value. So we know that h over the empty value of our mystery monoid is going to be 0, which is the zero value of the empty value of the integer monoid with addition. And because it's h is a homomorphism, we know also that it must respect the monoid operation of the integers. So for example, if we take two values that we know about, so doing 5 plus 5 is the same as, by the equation here above, is the same as combining these two values, but h here must respect addition, and so we can pull h out. And so we pull h out and replace it with the monoid operation of the mystery monoid. Since I have no idea what it is yet, I'll just call it op and use that instead. And we can now generate more values here, apply the same technique over and over again, as many times as we want. And since all the values here on the left are unique, so are the values on the right here. So effectively, we're generating values in our mystery monoid. So what do we have so far? We have the empty value of the monoid, and we have up-delimited chains of these weird values that were injected into the monoid. Now, the structure that we actually have here is obscured by bad naming, which I did on purpose. But if we rename it to something more suggestive, we can see that what we have here is the structure of a list. So empty is just the empty list. Inject takes a unit value and just wraps it with a singleton list. And our operation of the monoid is just list concatenation. In general, what we just discovered here is called the free monoid. So for for an arbitrary A, the initial object is just a list of A's. Inject builds a singleton list, and the homomorphism is provided by the fold map function, which is known from the Haskell standard library. And the universality of the homomorphism in the universal construction provides us that we have no junk. That is, there are no elements in our new monoid that are not required to be there for the structure of the monoid, and we also don't have any noise. There are no there's no junk, because if there was any junk, the homomorphism here wouldn't be unique. We'd have more than one morphism, and we have no noise because so it means that we don't have any relationships between the elements of the new monoid that are not required to be there by the laws of the monoid. And so we managed to. So what we have here is the minimal way to build a monoid out of any A. So by exploring a new category, which was the embodiment of unforgetting, we managed to learn something to deduce the minimal way to unforget. And circling back to the original quote from before, every time you see composition, there may be a category sitting to be found, waiting to be found there. And learning about the structure of the category can lead us to new insights, for example, the free monoid here. And hopefully the exploration of the monoid and the comma categories illustrated this point as well. Okay, so far we've been looking at concepts within specific categories. We see now how can we generalize concepts and move them between categories, and this will seriously boost our ability to explore the idea space. So here's the definition we had of the monoid that we had from before. If we take a deeper look at it, we see that it's kind of not portable in a sense that it's hard-coded to work with only the unit value, unit type, which is only available in the category of types. Similar to how programmers like portable code, mathematicians like portable definitions, ones that can be adapted to new circumstances easily. So let's fix it and generalize the monoid. Now the unit here is not the only problem. The product type is also very constraining. It's a very specific construction that really constrains what we can do with it. And so if we look back at how we use the monoids, we didn't really care whether we have two A's or not. We just cared to have some notion of two-ness inside this, this object, but we didn't really care how we got that. So any function of two A's will do for generalized monoid. So we will replace the product with what's called a tensor product. So a tensor product is basically any well-behaved function of two A's. And so this makes it much more generic, and we can apply it in various new contexts. Now we can actually tackle the unit here. So before I said that the unit is required so that we are able to point to specific elements of A, but that's only part of the story. The other part is the fact that unit is what is called the identity of the product. So product of A with unit is pretty much the same thing as just A. We would like to have something similar for the tensor product. So we would like to have some object called I for identity, which when tensored with A will be the same as A. So each tensor product will have its own version of I, but we can now replace our unit with this specific object, which is the identity of our tensor product. And now this definition is very, very generic. You can just move it around into very different contexts. Since we're no longer referencing the category of types. Now to illustrate how portable it is, I'll try to introduce a new category, the category of ender functors. Everybody knows where I'm going with it, I guess. Sorry. So our objects are going to be endofunctors, what the category theorists called endofunctors. Confusingly, these are type constructors that have a functor instance in programming languages. So functors in programming is the same as endofunctors in category theory. So the objects are not regular types, but rather type constructors. And the morphisms are what is called natural transformations. So I won't delve into them more deeply, but in programming they're just functions, generic functions that take a type constructor take us from a type constructor F to a type constructor G in a generic way. So for example, the function maybe toList maps between the maybe type constructor to the list type constructor, and both of them have a functor implementation, so they are objects in our new category. Now for us to have a monoid, we need a tensor product. For this, I'll choose the functor composition. So our tensor is going to be applying G to some type A and then applying F to it. And we also need the identity of the tensor. So the identity functor is going to be the identity of the tensor product, since composing identity with anything is just the same thing that we started with. And with all of this data, we can actually build a monoid in our new category. So we start with our diagram of the generic monoid. And since we're working with functors, we're going to replace them with F, because functors. Next, the identity object of the tensor product here is going to be the identity functor. And since working with functors generically is a bit cumbersome, I'm going to quantify the whole diagram with A, meaning that this diagram applies for all A that you can provide to me. But now I can actually reference A inside the diagram and make it a bit more readable as a result. So now I can replace every occurrence of A with the actual A. So identity of A is just A. We can now apply the functor here to A and we have F of A. And we can also write out our tensor product, which is functor composition, which will be F of A. So what do we have here? So it will be slightly easier to follow along with code. So let's just rewrite do the same steps, but with actual code. So this is our generalized monoid in some sort of pseudo Haskell code. So first of all, we replace A with a type constructor F with the functor constraint. We then replace the functions with natural transformations of the appropriate type. So now we have functions for all A with the appropriate types that we have from this diagram. And we can replace the tensor product with functor composition. And this is starting to look familiar, I hope. And a quick rename shows that we just rediscovered, rather mechanically, the definition of the monad structure. And we can even derive the standard bind operation just by using the building blocks that we have here. And this is what gave birth to the now famous or infamous quote that the monad is just a monoid in the category of endofunctors. So generalizing and moving between categories is a very, very powerful technique. Look how far apart are the two concepts that we just connected. Can you imagine discovering the connection between monoids and monads without the wide perspective that category theory gives us? And what's great about this portability is that all of our derived knowledge about monoids can be adapted to this new category. So for example, free monoids now correspond to free monads, a very useful construction. Comonoids, the dual concept, are now comonads, which we just rediscovered comonads just mechanically. Also, I didn't talk about them much, but all of these abstractions come with laws and proofs, and we can port those as well into our new category, and maybe in a sufficiently advanced language, we can actually reuse the same code that we use for monoids as well. So imagine achieving this level of reuse with just regular code and without category theory to guide you. So now we're ready for our last part. So I'll try to get a bit closer to code and show how the techniques that we learned so far can be applied to programming. As this quote implies, it would have been astonishing if you weren't able to find something useful in this study of composition. So it's not an actual case study because there isn't any real case, but nonetheless, suppose you're writing some code, a code that takes a list of something and produces some monoid, and you painstakingly kind of write out the code, how to do the recursion, and kind of go over all of the elements, and that's kind of annoying. But then you recall that list is the free monoid, and so from its initiality in the relevant category, you have fold map for free. And so now we can actually just describe how you process every single A, and then the fold map will just take care of a list of A's generically for us, which saves us some trouble of writing recursion, which is always good. But why stop here? We just learned to generalize, so we can move on to the category of antifunctors. And so now we have a new type signature that works on free monads. And this is actually a very useful function. It actually exists in libraries. And so one of the basic building blocks for working with free monads. We now also know about duality, so we can dualize this type signature. And now we just rediscovered some new concept, a free comonad, which is, again, a useful concept that can be used in various contexts. And look at these three type signatures and what an amazing journey through the idea space they imply. These are the sort of exploration tools that category theory gives us. Speaking of which, we can now take a step back and kind of admire what we have so far. So we started out with the familiar concepts of products and monoids, and we saw three techniques: duality, that lets us generate ideas for free from existing ideas. We saw how initiality gives us the free monoids. And we also saw how we can generalize and move ideas from one category to the other, producing monads. And we can keep on applying these tools in various ways, just as we saw in the presentation. More and more and even more. But this is just scratching the surface. Category theory provides us with so many other tools as well. For example, the Yoneda lemma, junctions, con-extensions that were referenced at the beginning of this talk. And all of these are reusable components that you can actually mix and match as you go along. You're producing more and more interesting ideas, going further away in the idea space, reaching ever expanding areas. So imagine having all of these tools at your disposal. What sort of things will you be able to discover using category theory as your tool for thought? I hope that many other things. And since this is all I have for you today, I'll leave you with a rather cryptic quote to ponder about at home. One day I hope to make sense of this. Thank you.